Hello AP Calculus AB and welcome to the big reveal. Today's title is Day 73, the area or accumulation function. And although that is a focus of today, there is a different title that I could have used, but we'll address that at the end after our big reveal. What is the big reveal? The big reveal is finally going to connect our idea of definite integrals to indefinite integrals and hopefully give us a shortcut to determine the area between any function, whether it's a nice geometric one in terms of shape of area or not. So we're actually going to focus on functions that do have nice geometric formulas to find their area, and we are going to discover that connection on our own. Let's rock and roll. There are three definite integrals on the opener. Your goal is to determine the area beneath each curve. Of course, noting that we are looking for the area underneath the curve of 10. So you might want to, somewhere on your paper, sketch the graph of y equals 10. It certainly does not have to be perfect. And we'll see what you guys can come up with. Try each of these, and then once you're done, unpause and come back together. Ready, set, go. Alrighty. Hopefully you sketched in a graph of y equals 10, something like this. Okay. And then on our first definite integral, they said we're looking for the area from 4 to 5. So let's say that this is 4. We'll see 5. We need 6. We need 7. So 5, 6, and 7. The area from 4, darken that. We'll use that every time. From 4 to 5 is just a 1 by, don't forget the height is 10 over here, right? So this area, whoops, as we slide across the screen, is just 1 times 10, which is 10. Easy enough. All right, our second area wants the area from 4 to 6. So that's going to be this guy. That looks like it's going to be 2 times 10, which is 20. And then our last area from 4 to 7, looks like it's going to be 3 times 10, which is 30. Now, I'm hoping that you can see a pattern here, right? We went from 10 to 20 to 30, and my guess is, and you don't need to write this unless you'd like to, but if I asked you for the integral from 4 to 8 of 10 dx, you could probably say, hey, I bet that's going to be 4 times 10, which is 40, and you'd be 100% correct. Nice. Well, anytime you have a pattern of outputs, you might start to think about this in terms of what is staying constant versus what changes, and we can use those to determine a pattern of outputs and maybe even sometimes inputs. So let's examine these definite integrals up above. Let's start by thinking about what stays the same, what stays constant, right? We should definitely notice that this lower limit of integration stays the same. We're always going from 4 to some value. Also, the function, of course, stays the same. The dx stays the same. The integral stays the same. In fact, what are the only two differences? Well, the only thing that stays the same in what was typed on your paper is the only thing that changes, rather, is the upper limit of integration. However, there is one other thing that changes each time, and the one other value that changes is the answer. So you're telling me that we have an input which changes and an output which changes? Doesn't that kind of sound like a function where we are changing this input and the output is depending on what we change the upper limit to? And so we enter our area or accumulation function. So named because as we change that upper limit of integration, we accumulate more area. If we were to change the 7 to an 8, now instead of accumulating or adding up the area from 4 to 7, now we add up the area from 4 all the way over to 8. We are also going to introduce a different variable, and we're going to try and explain why that happens. So let's analyze our area or accumulation function. We'll start from left to right. A is going to stand in for the area function. Okay, typical capital A. You can use any variable you want. You could call it f of x if you wanted, though that gets a little confusing as you're about to see. And this output is going to measure how much area accumulates from A to x. What is A? Well, A is the beginning of our interval. We held that constant. That was 4 in our examples up above. What is x? X is the thing that we're varying. X right here and also right here is the independent variable. That is the thing that we change each time. Now, you'll notice that inside the integral, the integrand, this f of t thing right here, uses a different variable. Why is it using a different variable? Well, up above, we used the function 10, and there wasn't anything too confusing. But what if that function had been 10x? Right? We still could find the area. You could graph y equals 10x. That would make some sort of diagonal line, and you could find the area. It's going to be like a triangle. But we wouldn't want to write it as 10x because we're already using the variable x. We're using x up here as the thing that we are varying, as the variable we're replacing with a number. And notice that we did not ever change the 10 that's inside. So we're not going to be changing this x that's on the inside. Rather, we're just changing this, and we want to make sure the inside function stays the same. It needs to stay 10x every time. And so to make sure we don't confuse these two variables, we use what is known as a dummy variable. T in here is our dummy variable. It's most commonly picked as t. You can choose any variable you'd like. So if you wanted to use q or z or anything like that, that's totally fine. But whatever variable is in this function, it needs to be different than the variable that's written up top, or that this is a function of. And that will make more sense on our next example, so no stress. F of t is still the function for which we're finding the area between that and the x-axis, and then our variable at the end needs to match the variable inside. We've always said that so far, and today we're going to find a different interpretation, but that's totally fine. Alrighty, so how can we write the opener as an area or accumulation function? Well, that's very easy. We're going to say a of x. The area found after varying any x value is given by the integral from 4, that was constant, to x of 10 dt. And hopefully in here we can see what's constant and what's going to change. Constant, that's where we start. Constant, and it's a function of t. This is what we changed every time, right? We made this 5, then 6, then 7, and area is going to be our answer. So how do we write this in terms of function notation? Well, we had 3 examples up above. I'll do one, you guys do the other 2. This was 5, which means we replaced the x with 5. So this becomes a of 5 equals the integral from 4 to 5 of 10 dt. And that answer that we saw up above was 10. Okay, go ahead and fill in those other 2, and then we'll discuss. Ready, set, go. These other 2 shouldn't be too terrible, and I don't think I really need to talk you through it. Most of this is just notation, right? Not designed to be too terrible, and I'm going to skip the intermediate step on this last one. A of 7 was 30. Now, we're going to go ahead and look at that main pattern from the opener, which is the pattern of the outputs. Okay, so although we said that there's all this stuff in the middle, right? We're finding an integral by calculating the area underneath the curve. If we took away that step and just looked at the inputs, right, the upper limit of integration, and the outputs as just individual numbers, we took away calculating areas and we just looked for patterns. We already said how you could predict the pattern. We said, okay, cool, well, this is 7, 30. I bet the next one is 8, 40, and the next one's 9, 50, and you'd be 100% correct. But we've analyzed patterns before. Now, in fact, we did a lot of this on our sigma notation day. No worries, no sigma notation right now. But one thing we did with patterns, especially patterns that went up by a common difference like so, is we wrote formulas for them. So couldn't we, if this adds 10 every time, write a different function? We're going to call this function maybe g of x. I just named it down here. Couldn't we write a function with this input that gives us this output that doesn't use an integral? Because this function looks linear to me. So couldn't we say that g of x equals, let's see, how do we write an equation for this? If it goes up by 10 every time, we discussed how that's going to be the slope. This is linear, 10x. And then we see if we're right. So if we take 5 and substitute it in for x, is 10 times 5 equal to 10? Ooh, no. 10 times 5 is 50. To make it equal to 10, don't we need to subtract 40? Let's see if the next one works. 6 times 10 is 60. 60 minus 40, isn't that 20? Yeah, I think we found our equation. Okay? So we have g of x equals 10x minus 40. And this equation, and I'm actually going to write these two down below, right? So we have g of x, which was equal to 10x minus 40, versus our area function, which was the integral from 4 to x of 10 dt. These functions are the same. They don't look the same, but they are two different ways to do the exact same thing. And hopefully out of those two, you're thinking this linear function is quite a bit easier than the area function. What do we want to do today? We want to determine how could we convert the area function that's here into this nice pretty little function over here. Is there a connection? So I don't want to spoil this for you, so what I'd like you to do is to take the next 30 seconds or so, compare these two, and think, is there a way you could have turned this function into this without doing too much work? So look at those, take 30 seconds to jot down an idea or two, and then we'll come back together. Ready, set, go. All right, hopefully you found a connection, but if you didn't, that is okay. Again, I'm not going to write anything here because I don't want to spoil things. We're going to try 2 more of these, and hopefully at the end of trying 2 more of these, you will feel much more comfortable, and then we have our big reveal. So let's try another. Given that f of t equals 2t, consider the accumulation function a of x equals the area starting at 0, going up to any x value we'd like, beneath f of t dt. And if you wanted to rewrite that slightly, you could also say it's from 0 to x. Instead of f of t, that's the function 2t dt. All right, so your goal is to find a of 2, a of 3, a of 4, which means we're replacing x with 2, then 3, then 4, which means we're calculating the area underneath the curve y equals 2t from 0 to some value. We should probably graph y equals 2t to see what the heck is going on here. Okay, so we have a t-axis and our y-axis up here. Y equals 2t is going to look something like this. Doesn't have to be perfect. And we have a few values which we are interested in. We have 2, 3, and 4. Okay. It looks to me, if we just wanted to determine the a of 2 over here, a of 2 equals, I'll probably need a little more room than that, so we'll just base it off this one. The area from 0 to 2, right, our x substituted in for the upper limit of 2t dt is going to be equal to, well, let's see, from 0 over to 2, and then the area beneath the graph. That looks like triangles. In fact, I think all of this is going to be triangles for today. So this looks like an area of 2. How do we find the height? Well, whatever the input is, the height is 2t, so twice the input. The height is 4 here. So I think we're going to do 1/2 times the base times the height, half of 8, which gives us a total area of 4. Using that, please go ahead and calculate the other 2 areas for B and for C. Alright, we're back. Hopefully you had some success here. I will show the math, but if you're comfortable, you can just skip on through. No reason to let me drone on about things you already know how to do. So I think our next one, a of 3, is of course going to be the area from 0 to 3, right? Something like this. If this input is 3, then the output is 6, so it looks like we have a base of 3, and a height of 6. So we have 1/2 times the base times the height. You could do this a different way. You could do half of 6, which is 3, so it becomes 3 times 3, which is 9. Or you could have said 18 and half of 18, right? And then we have one more of these, a of 4. A of 4 goes over here. This looks like we have a base of 4, and the height is being doubled every time, so it's a height of 8. And so we end up with 1/2 of 4 times 8. Half of 4 is 2. 2 times 8 gets us 16. Alrighty. Let's look at this as an input-output table. So we had 2, 4, we'll just stick with blue, 3, 9, 4, 16, right, just from our outputs that came up over here. And we're going to do the same goal as before. Let's find an equivalent function for a of x, and I'll remind you up above that a of x was the integral from 0 to x of 2t dt. We're going to find an equivalent function g of x that doesn't use an integral. And to do that, we're going to forget everything we've learned this year and even the year before, and we're going to go back to either Algebra 1 or probably Algebra 2, because if I look at this function over here, we'll notice that this function does not go up by a common difference. We start by going up by 5 and then by 7. And so what ends up happening, and there are two ways to look at this, I'm going to give you the maybe more challenging but probably more thorough way first, is we're going to go up by 5, then by 7, the next one goes up by 9, and so on and so forth. We're going up by a difference where we add 5, then 7, then 9, then 11, then 13. We're going up by odd numbers every time. But another way we can phrase that is that our differences are increasing by 2 every time. There is a common second difference. And anytime you get a common second difference, we know that our equation is going to use a second power. And this really does have to do with derivatives. If you take the derivative of a linear function, you get a common first difference. You get a constant, right? The derivative of, let's say, 10x is 10, so you'd be going up by 10 every time. However, if you take the derivative of an x squared function, I'll write this over off on the side, right? If this is our original function, then the first common differences go up by 2 every time. And the second common differences are a constant of 2. Nice relation back to Algebra 1 with those common differences, if you will. So by the fact that there's a constant here, I know then that we have an x squared or a quadratic function. However, you also could have seen that by realizing the relationship right here. Isn't the number that's here just the square of the input? And so I think we can say that g of x is just x squared, because if you substitute in 2 and square it, you get 4. 3 squared is 9, 4 squared is 16, and that's it. So this simple function right here does the exact same thing as the area function, and so instead of drawing all these triangles that we did up above, we could have just taken our inputs and put them in. But same question as before, we only have one of these left. Is there a relationship between these two that you can see? Hopefully there is, and if there is, you could have jotted that down, but let's do one more. Given that f of t equals 2t, wait, didn't we just do this? Consider a new area function, which I called capital B of x, from 2 to x. Oh, we changed the lower limit of integration. Was that going to change our answers? Maybe one more quick graph. We've seen this graph before. Something like that. And like this. And now we're starting at 2, and we're going to have to be plugging in 2, then 3, then 4. Let's see if this is different. So b of 2 is going to be the integral from 2 to 2, and then f of t is 2t in this case. Well, we actually already know how to do this. This is one of our properties of integrals. When we integrate from a value to the same value, we know that the area is always 0. Or visually what's happening is we're starting at 2, and then we're ending at 2, so we're trying to find the area of this line. This line does have some height, right? This is the point 2, 4, so it has a height of 4. However, it has a width of 0, and 4 times 0 is 0. Okay, our next one, b of 3. Well, this one means we're looking at the area from 2 to 3, beneath 2t dt. So from 2 to 3, the area here is this guy. Oh, look, that's a trapezoid. Wait, you're telling me trapezoids still exist? They do. Average of the bases, where my base is, right, this is 3 comma, we have to double that to get 6. So this is a height of 6 over here. So the average of 4 and 6, which you can just say is 5, times the height, and the height in this case is just 1. So we end up getting 5, I think, right? Nice. Okay. Last one, b of 4. B of 4 is over here, so let's erase this extra part without destroying too much of my graph. Did it? Okay. So this last one, I didn't mean to do that color. That's awkward. Let's go ahead and do it in yellow. There we go. So our last one is going to be this area, which is again a trapezoid, except this time we don't have a base of 1. We have a, or rather a height of 2, and then this guy over here is 4 comma 8. All right, so we have the average of 4 and 8 times the height, which is the base here, kind of strange. Those cancel. 4 plus 8 is 12. Same thing as before. We said that b of x was equal to the area from 2 to x of 2t dt, which is really, really similar to our function up here, right? Except instead of 0, we're starting at 2, yeah? And so we need to fill these in. So we had 0, 5, and 12. Okay, so this one went up, let's change colors, went up by 5, then by 7. Oh, it's that same pattern before. The next one's going to go up by 9. So there is a common difference of going up by 2 every time. Okay, so if we wanted to write this function, as before, we might assume it's the same function because it seems to be the same. It has that same pattern. But then if we try 2, 2 squared is 4, not 0. But just think of it like we did with our linear functions. If it doesn't work, just throw a constant in to make it work, right? 2 squared is 4. How do you turn 4 into 0? Well, you subtract 4. Does that work for our next one? 3 squared is 9. 9 minus 4 is 5. 4 squared, 16. 16 minus 4, 12. Great, we were able to write that quadratic equation pretty easily. Alrighty. Let's compare those 3 functions really quickly, and I'll start with our most recent, and then we'll work backwards. So b of x was the integral from 2 to x of 2t dt, and that gave us a function g of x equal to x squared minus 4. Okay, we saw earlier that we had the function a of x, which was a very, very similar function, except it's 0 to x of 2t dt, and that resulted in a g of x, or a function without an integral that was just x squared. Okay, and then on the first page, we had another area function, which was the integral, and I don't remember what it started with, so it started with 4, there we go. So it went from 4 to x of 10 dt, and our g of x function was 10x minus 40. What are those connections? Connections. Take a quick second, write it down. Can you come up with a way, a formula maybe, to convert our area function into our g of x functions? And if you want some further help here, maybe you could think of this as 10x minus 10 times 4, or this x squared function as x squared minus 0 squared, or this function over here is x squared minus 2 squared. And then you may even start looking at these values and these ones, these values and these and these. And then you might start even comparing the relationship between these guys. Hopefully it's clicking for you right now, but if it's not, that's totally okay, and we've got the big reveal on the next page, and you'll be even more surprised. But if you found it, good on you. Here we go. The big reveal. The Fundamental Theorem of Calculus, putting the fun back in calculus since the late 1600s. We need 2 quick reminders here before we do our big reveal. And the first one is, how is f of x related to lowercase f of x? Well, a capital F of x is the antiderivative of f of x, right? This is what we practiced the first 2 weeks of school. We said if you had something, and I'll give you a really easy example over here that hopefully doesn't give too much away. If you had something like 2x, then capital F of x was x squared plus c. Okay. And also, there are two types of calculus that we know. There is differential calculus. That was our focus last semester. They're derivatives which measure the rate of change, specifically the instantaneous rate of change. And then there's integral calculus, where integrals measure the area under the curve. Now, the crazy part about these two is they've been known for a long time, right? So we say calculus was, quote, invented in the late 1600s. People knew how to do differential calculus for hundreds of years before that. They also knew how to do integral calculus for arguably thousands of years before that, right? The Greeks alone, right, we're talking, over 2,000 years ago at this point, were able to calculate the area under the curve using infinitesimals. So they were using infinitely small rectangles. And the 14th century especially, there was a huge push for the study of motion and instantaneous rate of change. That's when they really started trying to map out the stars, predict eclipses and everything like that, and they needed to figure out how fast things were moving, and derivatives were a great way to do that. So why was calculus so fascinating? Well, it's because there was no connection between these two. Right? People were like, cool, we can find areas to do one job. And others were like, cool, we can find, instantaneous rate of change to do other jobs. But they're completely unrelated fields. How would anyone connect them? Well, that's what calculus did. So in the late 1600s, the Fundamental Theorem of Calculus would really come up, or its inception was from James Gregory and Isaac Barrow. And they actually predated Sir Isaac Newton, right? Sir Isaac Newton was the student of Isaac Barrow. And so, although these two kind of conceptualized the idea, they weren't really sure how to prove it or even too much of what they could do with it. It wasn't until we got Sir Isaac Newton and Gottfried Leibniz that actually formalized and proved how areas and instantaneous rates of change are related to each other. Now, there are a couple proofs out there, and the proofs are absolutely understandable by you. I do go in a slightly different order than I think most people would do. Many people teach the mean value theorem for integrals before this, and you're like, mean value theorem for integrals? Well, we learned one for derivatives. It should make sense that there's one for integrals, and we will learn that in a bit. However, the proof is really beyond the amount of time we have for this class, so I will post a couple links to some good proofs for it, and there's a nice proof in your book, 388 to 389. Khan Academy does a very nice, understandable proof, but I'd say maybe don't tackle those until we do the mean value theorem for integrals. But even though we aren't going to look at the actual proof, I feel like with that exploration on the previous 2 pages, you've kind of proved to yourself what the connection is between instantaneous rate of changes and area. Now, there are technically 2 parts of the fundamental theorem as well, one having to do with taking the antiderivative and one having to do with taking the derivative. We're only going to look at one part today, the antiderivative part, and then we're going to look at what I call part 2, 2 classes away from now. It really depends on who your teacher is and how they like to explain the proof of the Fundamental Theorem of Calculus for which part they teach first. Some will teach both in the same day. I like to split it. But either way, just trying to, diatribe a bit about why certain people teach this differently, because if you've come across this before, you might say, oh, my teacher showed me this first, and your teacher was probably right, and maybe I'm wrong, or maybe I'm just showing it a different way, and we're both right. So here we go. Without further ado, the big reveal. The Fundamental Theorem of Calculus allows us to quickly calculate the area underneath any graph, disclaimer, for which we know the antiderivative. Look, we're bringing antiderivatives back into area, and we do this by, instead of drawing a graph of lowercase f of x, we take the antiderivative of f of x, and then, well, can we figure it out just based on what we did over here? Isn't the antiderivative of 2t, ignoring the variable, isn't the antiderivative of, let's call it 2x, x squared? And then what did we do once we found the antiderivative? Didn't we substitute in the upper limit of integration and the lower limit of integration into x squared and just subtract them? And that is actually the first part of our fundamental theorem of calculus. It says take the antiderivative, substitute in the upper limit of integration, and then subtract the antiderivative evaluated at the lower limit of integration. And guess what we've done? We found the area underneath not just the basic curves we did at the beginning, but under any curve. X squared, this works. 1 over x, this works. Sine of x, this works, and that's it. No more drawing 16 different rectangles and saying, well, I drew 16 rectangles, it was an arduous process, and I still didn't find the right answer, but I was pretty close. This is the exact answer. Now, you might be looking at this going, but wait, why did we just spend 5 days drawing a million rectangles and trapezoids and sigma notation? And I'll give you a couple reasons for it. First, it says calculate the area underneath any graph for which we know the antiderivative. There are many functions which we don't know the antiderivative for. Right? E to the x squared, don't know that. A lot of us probably don't know the antiderivative of natural log. Okay? So there are definitely times where we're still going to use that approximation process. In fact, a lot of times when we analyze tables of data in the real world, there aren't perfect functions that fit those. And so we have to use these approximation methods to still calculate the area under the curve. The other reason that we study that is because it's very important to understand how this process evolved into finding the actual antiderivative, and in particular we need to know that summation definition of the integral, right? The one that we learned last class where it looks something like this, right? We go from k equals 1 to n, and then there's the f of whatever times delta x, right? A plus k times delta x. You are still expected to know that. And I found if I just shove this in my students' faces without any sort of background, that it makes no conceptual sense. So I really do like to build up to that, realizing that this is exactly equal to the integral is cool, but realistically, this big reveal is what you're going to use 90% of the time when you calculate integrals. Okay, so to find the area on a closed interval from a to b of an integrable function, integral meaning our function is continuous or has some countable number of holes, you take the antiderivative and then you evaluate f of b minus f of a. There's a little bit of notation in here, and that's what we're going to cover on the last page. So let's go ahead and take a peek. Okay, we're going to calculate the area from 2 to 5 of the function 2x dx. How do we do it? Well, quite easy. I'm going to introduce the notation of 2 square brackets like so. There are other notations that are used, and I'll cover them on the next page. First step, we find the antiderivative of this guy. Antiderivative of 2x, x squared. However, we're not done yet because that's a function and we know this is the area which is going to be a value. So we take our two limits and we keep them at the end, 2 to 5. This is kind of an intermediate step, and you should show this step every time you calculate the integral, because oftentimes on a free response question you're going to get points for just finding the antiderivative, and if you skip past it and do the next step wrong, you won't get any points. But if you at least get the antiderivative right, you'll sometimes get 1 or even 2 points. What does the fundamental theorem say, though? The fundamental theorem says once you've found the antiderivative, this is capital F of x, substitute in the upper limit first, so 5, and we still have a squared, and subtract the lower limit, 2 squared. So the integral from 2 to 5 of 2x dx is given by 25 minus 4, which is 21. That is the area underneath the graph of 2x. We would have had to use trapezoids if we did that earlier. It's very related to the most recent exploration on the previous page. But gosh, that was quick. Let's try one more. Let's find the exact area. We haven't been able to do this before. The exact area underneath the graph of sine of x from 0 to pi. We haven't been able to do this because the area isn't a perfect circle or ellipse or anything like that. So let's use the fundamental theorem. Okay. So the integral from 0 to pi of sine of x dx. Antiderivative of sine. Be careful, it's not just cosine, it is negative cosine of x from 0 to pi. Okay. Showing you a little bit of a shortcut here, and I'm going to rewrite this just so we can see what we're doing. I'm going to factor this constant out. That negative isn't going to affect anything, so I'm going to factor out that constant, and we're still going to calculate from 0 to pi. Okay, so what are we doing here? Well, we're going to go ahead, keep the negative out front, and be very careful with your parentheses here. Things are going to get weird. I want to go ahead and call this cosine of pi minus cosine of 0. And again, we're getting those by just doing the upper limit and then the lower limit. It's always upper minus lower. Has to be that order. You go the other way, you'll get the opposite answer. It's a no-go. And so I think from here, we end up with, let's see, cosine of pi is negative 1. Cosine of 0 is 1. To me, this looks like negative 2, or positive 2. And I always find that wild. The fact that sine of x, which is all about pi's and rotations and unit circle stuff and root 3 over 2 and root 2 over 2, I always find it fascinating that the exact area from 0 to pi underneath sine is a nice number. It's 2. This is our fundamental theorem of calculus. This is as hard as it gets for today. I did mention some notation stuff, so hopefully some of you were saying, well, wait, if we had something, if you had asked us to find the antiderivative of, and we'll just do the one on the previous page, 2x over here. If you said, I want you to find the antiderivative of 2x dx, then you would have told us that that's x squared, and then you would have yelled at us for getting the plus c. So how come when you did the antiderivative from 2 to 5 of 2x dx, there was no plus c? Well, here's the secret. There is a plus c. And you're probably groaning like, oh my gosh, we still have to put a plus c? No, you don't. And now you're confused. So let's take a look. Antiderivative. Let's put the plus c in here. And then go from 2 to 5. This is our fundamental theorem of calculus in action. And let's start substituting these guys in. So we have 5 squared plus c, being very careful with these parentheses, minus 2 squared plus c. This gives us 25 plus c, distributing the negative, minus 4 minus c. What happens here? The c's cancel out. And because this will happen every time, because there is always a minus in the fundamental theorem of calculus, right? We'll always have a plus c at the beginning and a minus c at the end. We don't have to write the plus c. In fact, nobody writes the plus c when we do definite integrals. So instead of putting the plus c, everyone leaves it off. It's convention. If it makes you happy, you can put it there and then cancel it out, but it's really just extra work. On indefinite integrals, do we need to write the plus c? Yes, you do. Right? This is an equation, and it's a general solution to a derivative, and sometimes you might have to find the specific solution by substituting in. I mentioned some alternate notations as well. I would say my notation is probably the second most common, but it just feels more complete having both of these brackets here. The other two notations, and I'm just going to show it all in one, and it's your choice on how you'd like to do it. I'd argue that probably the most common notation that I see is they do the antiderivative, and then they just draw one line and go from 2 to 5. Okay, and if you wanted to compare that, that would kind of be like our Leibniz notation, right? Where they might say, you know, evaluate d dx of, let's say, x squared at x equals 2. We've seen that line thing before. Similar idea here. They're saying evaluate this at 5 and 2, and you need to know what to do with the 5 and 2. That is the same as my notation of x squared from 2 to 5, and I've also seen the notation where they just use one of these and go from 2 to 5. Any of those are the same. All of them end up in the same spot where you show 5 squared minus 2 squared. And as a heads up, you should show these 3 steps. So of course you show the beginning of the problem. You need to show one of these 3 steps so that you can get credit for the antiderivative. And then you should show the first step of when you use the fundamental theorem. I heavily suggest that you do not just say 2 to 5, 2x dx. I can do all of this in my head. That's 21. There is not a time in the world on the AP exam where that would give you full credit. So be careful with that. They want to see those 3 steps. They want to see you know how to take an antiderivative, and they want to see that you know how to use the fundamental theorem. From there, go straight to the answer. Awesome. All right. Last but not least, more talk on notation. What the heck are the integral and the dx doing here? We haven't even covered this. Okay. Well, we need to remember our summation definition that we actually just talked about on the previous page, right? The fact that you can calculate the exact area under the curve using this method. Okay. Well, we know, and maybe I should even draw some sort of picture over here too. That seems like the right thing to do. If we're going from A to B, and we have this guy over here. Okay, well, let's break the 3 pieces down. F of A plus K times delta X. Well, what is that? Maybe I should make a couple rectangles too, right? I think in this case of our rectangle, this is like the height, isn't it? Right? It takes some x value. Let's say that this point is A plus delta X, and if you plug it into your function, it gives us a height, right? This height right here is F of A plus delta X. So this is the height. In an integral, and I'm just going to rewrite that same integral a couple times, okay, it is written as f of x. It's the same thing in an integral. F of something, this is f of an x value. Cool. What about delta x? Well, delta x is, of course, the length of a subinterval, right? We usually call this the base. So again, rewriting that integral from a to b, f of x dx. This is the base. And we've actually discussed the difference between delta x and dx before when we learned u substitutions, when we discussed differentials. And we said really the main difference is that delta x is an actual tangible amount. So delta x is going to be, if we were picking a specific length, like let's say 1/2, or subintervals that are a length of 3 or something like that. In an integral, though, because an integral is the exact area under a curve, we write dx, we write the differential, because we discussed that the differential is the absolute smallest piece possible. We call it infinitesimally small. And so this dx right here is still multiplying. That's why I always like to put the multiplication to show you what's happening here. It's still multiplying, but it is infinitely small because we said last class that if you want to find the exact area, then you need to make the base infinitely small so you can have an infinite number of rectangles, right? dx might be like this little piece right here, right? The smallest base that you could ever possibly conceive, and then go smaller. And so actually, looking at this integral, don't we have a base and a height? And so I would encourage you to continue to think of a definite integral as still a base times a height, right? It is the same thing as this guy over here, just written in slightly different and certainly more succinct notation. Okay, well, if they're the same and we've kind of covered this guy here and this guy over here, we still need to cover this monstrosity at the end. So what does this mean? Well, this not only means take n and make it infinitely small, which means an infinite number of subintervals very much connected to the base, but we also have this summation right here, which means you do one calculation, you multiply a base times a height, and then you do another, and then you do another, and then because this is sigma, then you sum all of them up. Okay, well, if you're going to sum all of those up, where the heck does that come in with our integral here? A to b, f of x, that's a height times a base. Oh, wait. Do you guys think maybe this right here might be how they rewrote our sigma? Well, what does sigma do? It sums up each rectangle's area. So what does this squiggly line in an integral mean? It's actually the letter S, except it's an elongated S. It really is. It's an elongated S that stands for sum. What this means is you are summing up an infinite number of base times height calculations over a specific interval. So it is really nice to see those connections there. Now, just as a friendly reminder, although we are summing these up, we are not actually using this formula in this class. We are just using the fundamental theorem, what we did up here. And your homework is all about the fundamental theorem, but I think it is really worthwhile to continue to see the fact that an integral is a base times a height. And maybe now we have a second or even third interpretation of this dx at the end. On indefinite integrals, we said that the dx just told us what variable we were taking the antiderivative with respect to. And that's true. When you get to double and triple integrals, you get like a dx and a dy, and you'll get different functions in there, and you do need those. But now we're saying, well, it's really there because when we do a definite integral, it's the leftover notation of base times height, and then summing all those up that come from the definition of our definite integral. So thanks for sticking around for today. We actually only have a couple lessons left here, and this is now into our third part, where our first part was how to do antiderivatives in definite integrals. Our second part was all about approximating definite integrals, and this last part is using the fundamental theorem to tie both of those together. Excited to have you back next class, where we can explore U substitution a second time around.